the Gram-Schmidt procedure is a method for taking an independent list and converting it into an orthonormal basis. So if we start with some independent list of v's, v1 through vm, and we define the first element of our orthonormal list to be the normalization of the first one, and then we take each of the successive elements from our independent list and we subtract off the projection to the foregoing j minus 1 terms, and then normalize by dividing by its norm, then this will produce an orthonormal list. This is the Gram-Schmidt procedure. So just notice that this is equivalent to saying that we take E1 to be the normalization of V1, and then E2 is going to be, and now we're going to take V2 minus the projection of V2 to E1, the thing we already had, and then we're going to normalize this. And then we go on to the next one, E3, and we're going to take it to be, we take the third thing from our list and we subtract the projection of V3 onto all of the foregoing junk, and then we normalize the result, and so on and so forth. So that's the idea for the Gram-Schmidt procedure. And so the theorem is that this produces an orthonormal basis, and that the span of the resulting E1 through EM, so that we have, is the span of the original list. So let's see. For the proof, I'm going to define uj to be the projection of vj to the span of E1 up to EJ minus 1, like so. Okay, and so then EJ, as defined by the Gram-Schmidt procedure, is VJ minus the projection over VJ minus projection norm. And that'll save a little bit of writing throughout the proof. And so the proof proceeds by induction. So for the basis step, note that clearly we have the span of E1 is equal to the span of V1, because one is a scalar multiple of the other. And we definitely also have the case that the magnitude of E1 is equal to 1 because it's normalized by definition. All right, so now for the inductive part, we're going to take our inductive hypothesis to be that the span of V1 up to Vj minus 1 is equal to the span of E1 up through Ej minus 1. Okay, so let's see now. Well, since V1 up through Vm is independent, we know that Vj is not going to be in the span of the foregoing, because it's not going to be in the span of any of the others because it's independent. And then since we know that the span of the first j minus 1 v's is the same as the span of the first j minus 1 e's, as we wrote in the previous line, this means that we know that Vj is not in the span of E1 through ej minus 1. Thus we know that it's impossible for Vj to equal Uj. And that's important for knowing that Ej is well defined, right? So if Vj is not in the span of the others, then Vj minus Uj can't be 0, and then we don't have a 0 in the denominator. Okay, and so then we know that the length of Ej is correct. All right. Now, if we take k from the list of numbers that come before j, then the inner product between ej and ek is going to be, well, let's see. So what's our formula for ej? It's Vj minus Uj over the norm of Vj minus Uj. And so now I can pull out that denominator in front using linearity because it's just a scalar. And then I can pull apart Uj into all the things that make it up. So let's see, so we've got Vj against Ek, and then I have minus the first part of U1, which is going to be Vj against E1, E1, and then I have minus the next component of Uj, which would be Vj E2, E2, and so on and so forth. Oops. So these terms right here, if you put them all together, that's going to get you your Uj. All right. So then what do we have? Well, I'm going to be able to pull out all of those. Actually, here, let me do it the slick and dirty way. Let's see. So I'm going to be able to pull out each one of these coefficients from the inner product, right? So looks like that. And then we see that these are all going to be equal to 0, except for the one where we have Ek, Ek. And we know that that's going to come up here because we're choosing k to be in this list. So it'll appear somewhere in that list. So we've got our first term. And then we've got the only thing that survives from out here, and it looks like, let's see, Vj, and it's the one where the subscript on the E was k. And everything else was a 0. By orthonormality, we know that this is going to be equal to 1. And then we have that these guys cancel. So we get 0. Okay. So from the very beginning to the very end, we see that Ej is orthogonal to Ek. All right. So what else do we have? It remains to note that Vj is in the span of E1 up to Ej. So if we look at the span of the first JVs, this is going to be contained in the span of the first JEs. But both lists are independent, and so they both have dimension J. And so if you've got a subspace with the same dimension as the space of the containing, the same dimension as the containing space, then they have to be the same vector space, right? So if V is a vector space of dimension 6, the only subspace of dimension 6 is V. So that shows this containment right here is actually equality. The end.